So, welcome to our third lecture, which in this lecture we're going to be looking at lines and logs. So, we'll probably spend the first third of the lecture looking at lines, two-thirds, sorry, before looking at the final third going on to logarithms, and we'll introduce this idea of logarithms. So, in this lecture, we're going to pick up some of the ideas we've looked at in the last couple of lectures, and we're going to extend them into actually looking what they physically mean. So before we start, I'm going to first describe what a function is. So you may have seen something that looks a little like this before, which is a linear function. Or you may have even seen something that looks a little bit like this before, which is a quadratic function. So if you haven't seen these before, well, clearly you haven't been to the last two lectures because we've been using these functions in our lectures, but you might have seen them in a slightly different format. So what we're saying here with a function is something is always changing in x, or something is changing in its x, or is a function of x. So for example, in this linear function, we see that when x is changing, there is a change in x as the function is changing through x. Likewise, a change in x here means there is a change in the square term. There's also a change in this single term here in this quadratic function. So let's kind of extend these to see what we mean by them and when we put them onto some plots. So we'll start with the linear function. So if we were to draw a set of two axes, a little bit like this, and we call them y and x, what we can actually do is begin to describe our lines. So if we draw a straight line, which is described by our linear function, we can write our equation as a function of x here, which is ax plus b, or perhaps you know this better in the format of y equals mx plus c. So as you'll have been shown at high school, what we can do is we can begin to use this line to fill out the terms in this equation, or likewise, we could use this equation to fill out the terms in this line. So first of all, you may have seen previously at high school that we calculated m, which is the gradient of the line. So m is calculated by a change in y over a change in x. So we can say that m equals change in y over change in x. So that's quite simple. We've done this before. We'll explain later in the further lectures when we get into calculus why we miss out the c term here as this limits towards 0. We can also use this c term here to find out where we cross the y-axis. So this is done by substitution. So for example, if we were to say that we want to find out where the y-axis crosses the 0 point in the x-axis, we can say that y equals mx plus c, but we want mx, or x at least, to be equal to 0. So because this is equal to 0, we can say that y equals c. Likewise, we could find out where the x-axis is, and we can do this by some simpler rearrangement. So we have y equals mx plus c. So by simple arrangement, we can find that y minus c all over m equals x. And if we wanted to find our point on the x-axis where it crosses here, we would just need to use this simple equation, and that would give us our answer. So next I talked about a quadratic equation, or a quadratic function, which we often see in this format. And if we were to plot this, typically a quadratic looks a little bit like a U shape, a little bit like this. So if we put this y and we put this y and x, so we can now say that this is the function ax squared plus bx plus c as a function. But we could also say on the y-axis that this would be y equals it would be ax squared plus bx plus c. So if we remember last week, we were actually solving or factorizing our values. But what were we doing when we were doing that? Well, what we were actually doing is we were saying we want to find the point in which the line crosses 0. So we know that we want to find, well, we want to find the point where the line crosses 0 on the y-axis, which would be here. So what we've said is 0, because we've subbed 0 in for y here, equals ax squared plus bx plus c. So we've actually factorized last week. What we've done is we've found the answer to our solution when we found our two x's. So for example, if this had been x squared plus x minus 2 equals 0, and we factorized it to find our two factors where we said that x, well, we've got a 1 and a 2, so that would mean we have a plus and a minus. So we open our two brackets. If we just solve this, have an x here and x here. So 1 times minus 2, will that be right? Yes, no, we want a minus 1 times plus 2. So we have a minus 1 and we have a plus 2 in the brackets here. We can say that this equals 0. And what we can also say is we then have two solutions to our problem. And as we can see with the quadratic, typically we have 2 points at which it crosses the axis. And we're trying to solve these two solutions. Likewise, if we go into cubics or quartics or even quintic equations, we'll have more and more solutions to the problem. So, but just for this quadratic at the moment, we have two solutions. And what we know is our two solutions will therefore be equal x minus 1 equals 0, or x plus 2 equals 0. So if we then rearrange these equations, we can find that x equals 1 and or x equals minus 2. So in the exam, what I'd want to see is I want to see that you gave me both answers to the question, because this would be the solution to our actual plot. Okay, so that has been just our introduction to some lines. In the next lecture, I'm going to introduce a technique called the solution by completing the square. And in this part, we're going to show how we can design or begin to design a rule that can help us solve some complex quadratics.